Okay, so in the previous video we talked about the idea of a stationary point being a point of zero gradient on the graph, and we did talk briefly at the beginning about how that might be a turning point or it might be a stationary point of inflection, given the kinds of graphs we've looked at so far. So three types of stationary points, and so when a question asks you to determine the nature of the stationary point, so if all you've done is show that the gradient is zero, then you just know that that's a point of zero gradient. To determine that it's a maximum or local maximum or a local minimum or a stationary point of inflection would require a bit more work or some knowledge of the function, okay, and or both. So three types of stationary points that we could get, and the first of those is a local minimum. Okay, so a local minimum would be where the graph turns around and has a minimum point. Now we refer to that as a local minimum. We'll talk more about this later on in the topic, because this point here, it's a minimum turning point, so it's a minimum within its neighbourhood, okay? But if you look at the whole function, it's not the minimum value of the graph. The graph gets lower over here, okay? So it's a local minimum because within its local neighbourhood, it is a minimum point. Same with this. This would be a local maximum. Up here within this region, it's a maximum point, okay? But if I were to look at the whole graph, there are points over here that are actually higher than that. So it's not the maximum value of the graph, not the maximum point of the graph. In some function types it will be. So in a parabola, this is both a local minimum and what we call an absolute minimum. It's the lowest possible point on the graph. But in something like a cubic, they're just going to be local maxima and minima. And in terms of determining the nature, the process we use is only going to enable us to decide whether that it's a local minimum or a local maximum. We would need to use a bit more logic to infer from that we know that it's an absolute maximum or minimum. So local minimum and local maximum, they're going to be turning points, okay? So this obviously gives the highest point of the graph within the neighbourhood, so it's a maximum. This gives the lowest point of the graph within its neighbourhood, so it's a minimum. I'll come to the second row in the table in a minute. We can also have a stationary point of inflection, and that can happen in two different directions. So we could be going up before we have that momentary point of zero gradient, or we could be going down before we have that momentary point of zero gradient. Okay, so what we want to be able to do to identify the kind of stationary point we've got is to think about what's happening with the gradient either side of the stationary point. So we know at the stationary point we have zero gradient. Okay, at the stationary point we have zero gradient. I'll use a different colour there. So at that stationary point the gradient is zero. At that stationary point the gradient is zero. At the stationary point there the gradient is zero. And at the stationary point there the gradient is zero. So by solving the derivative equal to zero, all we're identifying is that there is a moment of zero gradient at this point. To decide what kind of stationary point it is, we then need to look at what's happening with the gradient either side of that point. Okay, so in the case of a local minimum, before the point of zero gradient, the gradient is negative. Okay, I'm going to use minus VE to indicate it's a shorthand for negative. After the point of zero gradient, we have positive gradient. So if we have negative gradient followed by zero gradient followed by positive gradient, we must have a local minimum. Local maximum, on the other hand, we get positive gradient first, then zero gradient, and then negative gradient. When we have a stationary point of inflection, it's the same sign of gradient either side of the point of zero gradient. So the example on the left here, we've got a positive gradient, then zero gradient, and then positive gradient again. On the second example, we've got negative gradient, then zero gradient, and then negative gradient again. So what we want to do to determine the nature of a stationary point, if we don't know what the graph already looks like, there'll be times when you already know what it looks like and you know it's going to be a maximum because you're familiar with that function type. But if we don't know, what we want to do is consider what's happening with the gradient either side of the stationary point. And to set that up, we write something which we call a sign diagram, and we'll look at how we kind of present that and how we set that up. Okay, so let's have a look at an example here. So the graph of y equals 3x to the 4 plus 16x cubed plus 24x squared minus 6 has a stationary point with coordinates of 0, negative 6, sorry. Okay, so this question isn't asking you to find the coordinates of the stationary points. Now, it's also not suggesting that that's the only stationary point, but what we want to do here is to determine the nature of this stationary point. So okay, this is a positive quartic, but without having found all the stationary points, I don't know whether it's got, 3 turning points. I don't know whether it might have a point of inflection in one turning point, whether that might happen in another order, or whether it might actually be one of these, okay? So we want to determine the nature of this stationary point. So we don't need to find it, we're given that, but tell us what kind of stationary point it is. So let's set up a sign diagram to enable us to think about the gradient either side of this point and hence determine what kind of stationary point we have. So the sign diagram will be a small table and it will have 3 rows. The top row will be for our x value. The second row will be for the value of the derivative or the gradient at that point, okay? And the third row will be for us to identify what that means about the shape of the graph, okay? And then we're going to have 4 columns, well, 3 columns with information in them, but the fourth one with the headings, okay? And actually we will need another row, won't we, also for the information? Oh, no we won't. Sorry, my apologies. So we're going to have 3 columns. So we already know there's a stationary point when x equals 0. So the question is telling us that when x equals 0, the derivative is 0 and our gradient will be flat at that point. Okay? That's what we know. So to decide what kind of stationary point it is, we want to have a look at what's happening with the gradient either side of that point. Now you're just going to pick values that are in the neighbourhood of this point. You don't want to go for x equals 10 as a number bigger than this, because what might be happening is you might have a local maximum at 0. Let's say that's the point 0, -6, for example. Okay, and then you might have this happen, and if this is the point with an x coordinate of 10 and you calculate, well, there's positive gradient after this point, you've missed the fact that there was 0 gradient before there. So you really do want to stay very close by in the neighbourhood, but you also want to work with simple numbers if you can. So we'll probably look at when x equals -1 and when x equals +1. Okay. Now we need to calculate our derivative so we know what we're substituting into. Okay. So dy dx here is going to be 12x cubed plus plus 48, that's 3 times 16, x squared plus 48x. Okay, so that's our derivative. So then when x is -1, dy dx is going to be -12 plus 48 minus 48, so it's -12. And when x equals +1, dy dx, and you might be able to do these, if it's a simple derivative you can do the calculations in your head, but I'm just writing them out here to be clear I've got them right. When x is +1, I've got 12 plus 48 plus 48. Right, 48 plus 48 is 96 plus 12 is going to be 108. Okay, so when x is -1, the gradient is negative. So the graph is going down before this stationary point. When x is +1, the gradient is positive. It's quite a big positive value, and so it's going up at this point. Okay, so therefore we can say when x equals 0, the graph has a local minimum stationary point. Okay, and so we already know from the question that that's actually the point 0, -6. So 0, -6 is a local minimum point. Okay, be clear about the fact that you don't say x equals 0 is a minimum. The x coordinate's not the minimum value of the function. When x is equal to 0, the graph, there is a local minimum. The graph has a local minimum. Or you can write the point 0, -6 is a local minimum point. Okay, but be careful about the fact that x equals 0 isn't a minimum. It is the x value that gives the minimum value of the function. Okay, so we use the sign diagram. It's really important that when you set up the sign diagram, you actually have to calculate these numbers. Okay, it's not sufficient to just say this is negative and this is positive. Okay, we need evidence of that to justify that you know that this is actually a local minimum or a local maximum. All right, let's have a look at some other examples. So because in year 11 we're only differentiating polynomial functions, generally speaking we're differentiating a function where we know what it looks like, and so we should actually be able to determine the nature of the stationary point without needing to go to a sign diagram. Having said that, you must know how to do sign diagrams. We'll talk more about this in some applications. There are situations where you need to verify what kind of stationary point you have, and there'll be functions where you actually don't know what the graph of that function looks like. So the only way to determine what kind of stationary point you have is to use a sign diagram. Okay, so but as I said, in many cases, your knowledge of the function will tell you about the nature of the stationary points. So if you have a positive quadratic and it has one stationary point, so by positive quadratic I mean a is bigger than 0, so positive x squared term. So you know the shape goes like this if you've got a positive a. And so when it's got one stationary point, you know that has to be a local minimum. Okay. If you have a negative cubic with two stationary points, you know the shape of this graph is going to be that. And so therefore, the first stationary point is a local minimum, and then the second stationary point is a local maximum. So thinking about what you know about the shape of the graph. If you have a positive cubic, that is a is bigger than 0, so a positive x cubed term, with one stationary point, you know the only way a cubic has one stationary point is if that point is a point of inflection. And if you had a negative quartic with 3 stationary points, you would know that it's going to do something like that. So the first one has to be a local maximum, the second one has to be a local minimum, and the third one again has to be a local maximum. So being able to combine together your knowledge of the graph shapes with what you're calculating should enable you to determine the nature of the stationary points without necessarily having to use the sign diagram. As I said though, there are definitely places where you need to be able to generate the sign diagram. Example 2. Find the coordinates of the stationary point or points of that cubic and state their nature. Hence, rewrite f of x in the form a times x minus h cubed plus k. Okay, if you think about this, this is telling you something about what's happening with the stationary points here. But let's work through the problem. Let's worry about the hence. So when you see hence, think about that as sort of being part B of the question. Do the first part and then worry about what the second part's asking you, because it will probably become clear at that point. So the first part is to find the coordinates of the stationary point or points of this function and state their nature. Okay, so f dash x, we're going to need derivative for the stationary points, is going to be 6x squared minus 24x and plus 24, and that has to equal 0 for the stationary points. We've got a nice common factor of 6 there. Let's divide everything by 6, so that's going to be x squared minus 4x plus 4 equals 0. Okay, and that factorizes, that's x minus 2 all squared, and so x minus 2 equals 0, and so x equals 2. Okay, find the coordinates of the stationary points. Okay, so let's work out f of 2. F of 2 will be 2 times 2 cubed minus 12 times 2 squared plus 24 times 2 minus 14. Okay, so that's 2 times 8, that's 16, minus 12 times 4, so minus 48, plus 48, 24 times 2, and minus 14. Oops, 14. So the 48s are cancelling out, 16 minus 14 is 2. Okay, so therefore we have a stationary point at 2, 2. Now, it's a cubic with one stationary point, okay? So one stationary point for a cubic means it is a stationary point of inflection. Okay, and so once you've worked out that it's a stationary point of inflection, the second part of the question now makes sense. We know that we can only write cubics in this form if they have a stationary point of inflection. Okay, this one does have a stationary point of inflection at the point 2, 2. Okay, so therefore that means that our function is a times x minus 2 cubed plus 2. So we need to think about working out that a value. Now, you could, I don't know, you could work out that the y-intercept of this point is 0, negative 14. You could sub that in to find a. But actually, if you think about the fact that when you expand this out, it has to be the same as that, the only way you're going to get 2x cubed here is if a is 2. So the coefficient of x cubed in the original function will tell you that f of x has to be 2 times x minus 2 cubed plus 2. So if you were to expand all that out, it should give you the same equation as that. Okay. All right, and then example 3, which is accidentally listed as 2 in your notes, apologies. Find the coordinates of the stationary points of this cubic and state their nature and hence sketch the graph. Okay, so we're going to need to do a bit of work here. We've got a whole page. So let's do the first part, which is to find the coordinates of the stationary points. So we need the derivative. It's going to be 3x squared minus 12x plus 9. We want that to be equal to 0. Now, all the examples I've done so far have had a common factor of 3. Not all derivatives will have a common factor of 3, just so happens that these particular examples do. Okay, so we've got that quadratic dividing everything by 3. Factors of positive 3 that add up to negative 4 are going to be minus 3 and minus 1. And so therefore x equals 3 or x equals 1. Okay, so that's the x coordinates of the stationary points. So we're going to need to sub those x values back into the original to find the y coordinates. So f of 1 is going to be 1 minus 6 plus 9 minus 4. So if we think about minus 6 and minus 4 is negative 10, positive 1 and positive 9 is positive 10, so that's going to be 0. Okay, so that means that one of the stationary points has coordinates of 1, 0. F of 3, 3 cubed is 27, minus 6 times 3 squared is 9, 6 times 9 is 54, plus 9 times 3, which is 27, and minus 4. Okay, so 27 plus 27 is 54, so take away 54 is 0, and then we've obviously just got minus 4. Okay, so that is the point 3, negative 4. Okay, we're also going to need, let's think about, so this is our stationary points. We need our y-intercept. So that is f of 0, so that's negative 4. And we need our x-intercepts, which is where we're going to need to do a bit of work. So we need f of x to equal 0, which means we need x cubed, sorry, let me just scroll so I can see it, minus 6x squared plus 9x minus 4 equal to 0. Okay, so we're solving a cubic. So the first thing we need to do is identify a factor, and actually unknowingly, we've already identified a factor up here. We know that f of 1 is equal to 0, and so we know therefore that x minus 1 is a factor. So we're going to divide x minus 1 into the cubic to find the other factors. You might use synthetic division or a different division technique, that's fine. What do I multiply x by to get x cubed? That's x squared. Multiply x squared by x minus 1, so that's x cubed minus x squared, and then subtract. Negative 6x squared minus x squared. Negative 6x squared plus x squared is negative 5x squared. Bring down a term, adding 9x. So then what do I multiply x by to get negative 5x squared? That's minus 5x. Multiply minus 5x by x minus 1. And subtract. 9x minus 5x is 4x. And then we bring down our next term. What do I multiply x by to get 4x plus 4? And that's all good. We've definitely got a remainder of 0. Okay, so therefore we now know that our equation is, try and leave us with some space, let's go up here. So we now know that our equation is x minus 1 times x squared minus 5x plus 4. Further factorising the quadratic, that is x minus 4, x minus 1. So actually that already fits with what we know. So we can see that it's x minus 1 squared times x minus 4. X minus 1 squared means there's a turning point there, and that's why we found the turning point at 1, 0. Okay. So we have x-intercepts at 1, which we already knew, and at 4. Okay, so that's 1, 0, and that's 4, 0. Okay, so we've got all our information. We've got our 2x intercepts at 1 and 4. We've got our turning point at 3, negative 4. Our y-intercept at 0, negative 4. Okay, so let's think about our graph. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Y-intercept is 0, -4. X-intercepts are 1, 0, and 4, 0. And turning point is at 3, -4. Okay, so so we're going to have a turning point there and an x-intercept. We're going to turn there and then go through there. So labelling all of our intercepts with coordinates and our turning points now that we can do that with coordinates. And there is our graph. Okay, so exercise, I just want to be clear about what the question said, because I think it said, yeah, and state their nature. Okay, so again, we can worry about that once we've done the graph if we want, or you could have thought about the fact that you've got a positive cubic, therefore the first of the turning points, which has an x-coordinate of 1, will be the maximum, and the next turning point after that will be the minimum. Okay, so this one is a local max, and this is a local min. Sorry, I just realised we hadn't quite answered that part of the question. Alright, so exercise 18D is the work for today.